ISRI, Indian Society of Heating, Refrigerating and Air Conditioning Engineers. Founded in 1981 at New Delhi by a group of eminent HVAC and R professionals, ISRI now has a total of 41 chapters and sub-chapters.
ISRI gives you the latest industry insights of the HVAC and R and building industry and delivers latest technologies in forms of technical blogs, videos, and articles to people. It has more than 14,000 members and about more than 10,000 student members. ISRI releases various standards for HVAC and R building industry time to time. It organizes more than 800 events every year, including seminars, conferences, product presentation and more. ISRI also provides handbooks and guidelines. ISRI also has student chapters in more than 150 engineering colleges, to encourage students and let them know about HVAC and our industry. Visit now, isri.in, for more details.
Hello?
Hello.
Hello, can you hear me?
Yes, sir, we can hear you.
Okay, good evening, everybody. And this is Manjunath MS. I'm just going to make a brief introduction of today's speaker. He is a guru of refrigeration, Mr. Ramesh Paranspe. And here is the brief introduction of Mr. Ramesh Paranspe. He is a fellow life member of ASHRAE, and he has been in the industry and in the refrigeration field for over 50 years. And he has been honored by the ASHRAE Award for 50 years of service to the fraternity. Mr. Ramesh Paranspe is a MTech in refrigeration from IIT Bombay, and his professional experience has been tremendous. He has held leadership positions as a chief executive of Voltas, managing director at Carrier. Hello. He has over 27 years of experience as vice president of AC&R division at Kirloskar Pneumatics. He has published more than 45 papers in national and international journals. He has conducted more than 300 training programs at various companies, top-notch MNCs like Honeywell, Alpha Level, Voltas, Blue Star, Thermax, Emerson, etc. So some of his achievements, he has been invited by the German Chamber of Commerce to deliver lectures on ammonia pumps circulation systems. He is a specialist, a guru in refrigeration, and especially in ammonia refrigeration. He has been a member of the ASHRAE committee for the handbook. He has published books for Danfoss controls. He has published a book on air cooler designs for cold storages for alpha level, and has executed more than 700 projects for cold storages, ice cream, process plants, fish and meat freezing. So he is an actual, you can say he is the guru of refrigeration. So why do I call him a guru of refrigeration is because those who have already attended his previous 2 lectures will agree with me that he's a guru in refrigeration. And those who are new today, those who have just come in today, even for you all, when you hear him, you will definitely agree that he is a true guru. Mr. Paranspe has been kind and very magnanimous to offer his presentations at the end of these lectures. Those presentations are being sent to all the attendees in the form of a PDF file. So that should make us quite knowledgeable. But along with that comes a big responsibility, and that responsibility is about recalling and reusing this knowledge when it is required and where it is required. So, you know, recall and reuse of knowledge is called as wisdom. And to get that wisdom and to be wise after hearing and practicing the knowledge that Mr. Paranspe gives is the best form of thanks that we can give him back, because he is a true, in all true, you know, meaning of the word guru. He is a real guru in refrigeration. Last piece of advice: keep a pencil and paper with you, because whenever Mr. Paranspe gives his talks, on every slide he makes a few comments, and there is an ocean of wisdom in those comments. So when you get back and read the PDF slides, please take these comments and read it along with the slide. It will enhance your knowledge as well as make you more wise. Thank you very much, and over to Mr. Ramesh Paranspe.
Hello. Hello.
Yes, Mr. Paranspe, we can hear you, sir.
Yeah, you can hear me. Okay, good. So I will start my presentation. You can see my screen also.
Not now, sir.
You are able to see the screen. Okay.
You
So
just
can
need
you
to
see the
share your
first?
screen.
You can see, and you can see my screen also. Or you cannot see the screen.
Sir, still not, we are not seeing your screen. We are not able to see your.
You have to send me a message to share my screen.
I have just sent you again.
Okay. Now you can see.
Yes, yes, yes.
Yeah,
Now
now we can see.
Okay. Now I will start my presentation. Everyone can hear me. Okay. Very well. Good evening to all of you, and welcome for the third session of the seminar. First 2 sessions, I'll just recollect what we covered. In the first session, we covered global warming and the importance of selecting correct refrigerant to ensure that the global warming is restricted. And we came to a conclusion that ammonia is the right refrigerant. In the second session, we covered all the good properties of ammonia as well as some drawbacks and how to overcome those drawbacks of ammonia system. So in this third presentation, which is a little longer presentation, we are going to cover all the refrigeration systems in ammonia. I'm not covering any other refrigerant. I'm going to talk only on ammonia refrigeration and what are the systems which are used for ammonia refrigeration by various consultants, various designers, or various end users. So we'll go to the next slide. The next slide shows that this first I'm going to do little fundamentals because I always believe that if you want to learn refrigeration, it is very, very important that you master pH diagram, that is pressure enthalpy diagram, which is a very important diagram which we learn in our colleges in final years of engineering. But during subsequent period, during our practice in life, we forget about it. So since I teach also in college and also practice, I am firm believer that if you want to become a good refrigeration engineer, you must constantly follow the pressure enthalpy diagram. And that is very, very important. First, the refrigeration is a utility, but it is a different utility. It is not a utility like your tap water that you just turn on the tap and the water starts flowing, or an electricity that you switch it on and the lights come on. Refrigeration is a utility which takes time. The moment you start the plant, it doesn't give instantaneous temperature. It takes little bit of, maybe depending upon the system design, depending upon the process, maybe 1 hour, 45 minutes, 2 hours, like this. So it is a different utility. Let us look at this slide, vapor compression cycle. It is, last time I talked while talking to ammonia, it is lifting. It is on the right hand side. You can see tank B and tank A. It is lifting. It is like lifting water. Here in refrigeration, we don't lift water. We lift the heat. So it is a heat pump. Compressor acts as a heat pump. It pumps the heat from where it is not required to a place where it is not objectionable, that is sink, source and sink. And for doing this work, which is against the nature, because heat will flow from high temperature to low temperature, and we want to flow it from low temperature to high temperature, so we require energy, and therefore compressor requires energy. So the next slide will show you actual refrigeration system, which shows that the cold space and the atmosphere. I got few questions after my last presentation and which were forwarded to me, that how do we select our condensing temperature and how do we select our evaporating temperature. I had indicated that in my next session I'll clarify a little bit more, and that's why this slide shows that we want to maintain a temperature, a cold space at a particular temperature. And where do we reject this heat? Finally, we reject it to the atmosphere. Now, in order to have a heat transfer, you require certain temperature difference. If both are at the same temperature, heat will not flow. It is like water. If the two tanks are at the same level, water will not flow. Water will flow only from high level to a low level. Similarly, heat will flow also from high temperature level to a low temperature level. And therefore, cold space and atmosphere, these are the two yardsticks which determine where the heat is going to be rejected. The condensing temperature has to be higher than the atmospheric temperature, than the space to be maintained. This is very, very important. Now, if you look at this is a vapor compression cycle, and this is cycle known as Carnot cycle. Carnot cycle is a very, very important cycle. It maintains TC condensing temperature at 40 degrees centigrade when atmospheric temperature 35 degrees centigrade. And cold room is minus 10 degrees. So evaporating temperature in refrigeration system has to be lower than the cold room temperature. Then only the cold room cold will flow to the refrigerant. Now these two conditions are decided by our pH diagram, our other diagrams, but Carnot cycle does not recognize this. Carnot cycle is a theoretical cycle which has, if you see on the right hand side and the left hand side is a pH diagram, and on the right hand side it is a temperature entropy diagram. And if you see, there are two isothermal processes, that is 2 to 3 and 1 to 4 constant temperature processes, and two vertical lines 3 to 4 and 2 to 1, that is constant entropy processes. Now this is 100% theoretical cycle, which is a final cycle. In reality, it does not happen. You cannot run the plant with a Carnot cycle. The COP of a coefficient of performance of Carnot cycle is T evaporating, that is TL upon TH minus TL. This is just remember this Carnot cycle, and then we go to the next slide. The Carnot cycle is called as a king of cycles because it is a model of perfection of a refrigeration cycle, most efficient cycle between the temperature levels. As I had mentioned, two isothermal processes and two isentropic processes. Efficiency is independent of whichever refrigerant you use, because these temperatures will remain constant, whether you use ammonia, R22, 404A, etc. in a Carnot cycle. All the real cycles are compared, therefore, with Carnot cycle. It is also known as reversible Carnot cycle. Now we go to the actual refrigeration cycle, what we follow in the field. That is the pH diagram, pressure on the y-axis and enthalpy on the x-axis. And these are the four components of a refrigeration system. So which are the important diagrams we are going to look? We have already looked at Carnot cycle, then pressure enthalpy diagram, temperature entropy diagram, and the last is temperature enthalpy diagram. I'm telling you once again that if you master these four diagrams, you will be more than 95% best refrigeration engineers. You don't have to consult anyone. This is all available on these diagrams. This is the pH diagram. Look at the pH diagram. It shows evaporator, condenser, compressor, and metering device. Point 1 to 2 is an evaporation operation. Point 2 to 3 is a compression operation. Point 3 to 4 is condensing operation. And 4 to 1 is an expansion device. We will discuss this little bit in details, but see, look at the point 2, which is a this green line, what you see, a green line, which is a line, and that line is known as saturation line. All parts which are falling on the left of this line are liquid lines. All the points falling on the right hand side of green line are all vapor lines, and between the two green lines it is a mixture, refrigeration mixture. The top point is a critical point, and beyond that, if you go, you won't be able to condense the refrigerant, and that is what happens with CO2, carbon dioxide, as a refrigerant. The next slide, this is a T temperature entropy diagram. This is, if you see in the first slide, we did not see on the pH diagram very distinctly the temperature paths. Here you will be able to see from 2' to 2 that is a superheat which is being removed, and 2 to 3 is a condensing process. Also 3 to 4 on the pH diagram we saw as a constant enthalpy line. In reality, it is entropy. Entropy goes on increasing or changing. If you see any process which is taking place in the world, the entropy always increases. Therefore, they say that the entropy of the universe is constantly increasing because constantly some process is taking place. So we will not go into too much details of this. But we go to the next diagram, and this diagram you will find very important diagram. It is not available anywhere in most of the textbooks and in many places. And this is a diagram prepared by me long back. Therefore, it is in BTU units, FPS units, not in MKS units. But why I prepared this diagram? Because it combines both the TH diagram and a PH diagram. For example, if you able to see, there is a 10-degree superheat, you can see. Uh, uh, then you can see the compression process where the heat is getting added. That is the compressor work done from 110 to 125. That is 15 BTU. That is compressor work done. 10 degree Fahrenheit is a superheat. Then from 125, that is the cooling starts. First the superheat is removed, then the condensing takes place, and then the subcooling takes place. 15 degrees is a subcooling, and when the refrigerant is expanded, you again get a superheat here, which is on the compressor side. So subcooling, superheating, compressor work done, condensing, evaporating, everything you are able to see on this slide, which is an important slide. I will share this slide in my presentation as usual. This was an introduction, which is a basis which I wanted to first cover in first 10 minutes to take to ensure that you further are able to, especially those who are freshers and doing the job for the first time, they will be able to understand much better. Those who are already practicing engineers, for them it may be very fundamental type, but it was necessary for the entire people who are listening to this presentation. The four basic components for any refrigeration system are compressors, condensers, evaporators, and what we call liquid metering devices or the expansion valves. Expansion valves. And therefore, now we will concentrate only on the pH diagram. We will not look at TS diagram or Carnot cycle or any other diagram, because all our engineering is going to be, in reality, application engineers work on pH diagram. pH diagram allows us to see the invisible. It allows us to find pressure that matches with any temperature, saturation temperature, finds out all properties of refrigerant as we saw on pH diagram, superheat, subcooling, and desuperheating, etc., etc. Also, we also saw that what condition the refrigerant enters the compressor, what condition and compressor leaves the compressor, etc., etc. So use of one diagram for plotting performance of all components is important. This is a regular circuit, and if you see evaporator and condenser, I have put here the conditions, that is at the compressor outlet, that is high temperature, high pressure, and superheated gas, that is the discharge of the compressor. At the entry of the condenser, it is same. At the outlet of the condenser, the temperature, condensing temperature is high, but not as high as compressor discharge because the superheat has been removed. The pressure remains constant, which I have assumed. I have neglected the pressure drops in the heat exchangers. The subcooled liquid, here you get subcooled liquid at the outlet of the condenser. Subcooled or saturated. In ammonia plant, normally we get saturated liquid. At the entry of the evaporator, you get low temperature because expansion has taken place, low pressure, saturated liquid vapor mixture. How much low? We have already discussed. It has to be lower than the room to be maintained. If it is air conditioning plant where we maintain 23 degrees centigrade, then evaporating temperature has to be lower than 23 degrees centigrade. If it is a chilled water plant, we have to maintain, if the chilled water supply is 7 degrees centigrade, we want to maintain evaporating temperature around 3 to 4 degrees centigrade. In cold storages, we go to -5 degrees centigrade, like that. And then lot of especially field people say high side of the equipment and low side of the equipment. So what is the high side of the equipment? That is compressor discharge. This red zone is all high side equipment. That is compressor discharge, condenser, all the pipelines up to the expansion valve. After expansion valve, the expansion has taken place and evaporator is low temperature, low pressure, that is low side of the system, and its pipelines. So this blue zone is a low pressure side. This is a pH diagram, which is also known as Mollier diagram. This is from ASHRAE handbook. You will find this diagram in ASHRAE, those who are having ASHRAE handbooks. The next diagram is also ASHRAE, but I have plotted on that the conditions. That is entry to the compressor, outlet of the compressor, etc., etc. But the next diagram is very, very important. Now, this is a software which is known as CoolPack. Just remember, if you want to write down CoolPack, because this is a free software available from a Swedish institute, and it plots everything, whatever we require on a pH diagram. For example, if you see the point 1 as -5 degrees centigrade, that is evaporating temperature. But it shows the pressure drop in the evaporator. It shows at point 1 further pressure drop. Then compression takes place from 1 to 2. And then there is a pressure drop in the discharge line. Condenser pressure drop from 3 to 4. And 4 to 5 is an expansion. So it actually plots all the correct points of the systems. -5 degrees evaporating. And if you see the condensing as 40 degrees, which is I have taken as a normal Indian conditions. It shows corresponding pressure, it shows corresponding volume, it shows corresponding enthalpy, what is the enthalpy of that refrigerant, and the S value, that is entropy value. Now, having introduced all this, let us go to our system design, which is the today's subject. Why do we want to have, when we design refrigeration system, what are our expectations? We want, of course, highest efficiency. Then we want simplicity of operation. Operators should be able to operate the plant easily. Minimum refrigerant quantity, because we saw ammonia quantity has to be low. Ammonia is a toxic refrigerant. If large quantity leaks, it causes problems. Then next is value for money, that is owning and operating cost. Then life of the system is also important, 10 years, 15 years. Normally we assume 15 years. And finally, safety. Safety is also important. We are going to have our last session on safety, ammonia safety. So we will not talk too much of it just now. Now, what are the various ammonia refrigeration systems? Just look at it. Vapor compression systems. First part is vapor compression systems. All ammonia vapor compression systems we are going to discuss, and we are not going to discuss absorption systems or any other systems. We are going to discuss only vapor absorption systems, and in which there is a single stage system operating between plus 40 degrees, which is condensing temperature, and up to say -15 to -20 degrees centigrade. This is a limit for ammonia on a single stage. The two-stage system, you can go down up to temperatures -40, -50, -55 using the same refrigerant, ammonia refrigerant, either with uni-built compressor, that is Some compressors, some manufacturers build compressors where high stage and low stage cylinders are in the same frame, or two independent compressors, independent compressor for high stage and independent compressor for low stage. The third system is a cascade system where either you use two different refrigerants or the same refrigerant, one for high stage, another refrigerant for the low stage, and in the low stage, either you can use another refrigerant or any other fluid. Fluid could be any brine, that is calcium chloride, sodium chloride, ethylene glycol, etc., etc. And you can go up to minus 60 degrees centigrade. Just remember, when you go below minus 33 degrees centigrade with ammonia plant, the plant will be working under vacuum because that is the boiling point of ammonia. Now, having covered the single stage, two stage, and cascade, these are the three different types. What are the different systems which are possible as a designer? Direct expansion systems, gravity flooded systems, force feed, pump circulation systems, low ammonia charge systems, and this is a patented design of LVS system by JBT. We'll not discuss much about that, but since I have listed the different systems, I thought of mentioning that also. But we are going to discuss more on direct expansion, gravity flooded, force feed, and low ammonia charge systems. Lot of people have a confusion whether direct expansion is to be used or a gravity flooded system is to be used or a force feed system is to be used. So all that we will clarify in our next slides. Any refrigeration system, as we saw, that we have four components. Compressors could be reciprocating or screw, uni-builds, two-stage or two separate compressors. Condensers could be atmospheric condenser, old cold storages, lot of cold storages use still atmospheric condensers, shell and tube condensers, evaporative condensers, plate heat exchangers. But in India, mostly all these are water cooled because we have water available. In some areas like Middle East and other places, we have designed ammonia systems also with air cooled, but the efficiency is very low. But there is no alternative because water is not available. The expansion devices could be low side float valve, hand expansion valve, flow regulating valve, motorized control valve. These are all in the high pressure liquid line before the evaporator. And the evaporators are all application oriented. Remember, very important thing, that it is finally the evaporator which delivers the output. The condenser, compressor, expansion valves, all these are backups. It is like on the computer. Computer on the screen, you can see my presentation. But what the software has gone to build this computer and to make this possible, you cannot see it. Similarly, compressor, condenser, receivers, expansion valves, other things, only evaporator is in the cold space. Whether it is room air conditioner, you see the room air conditioner or a split coil or a cold storage air coolers or evaporator, any evaporator. These could be evaporators, could be shell and tube plate heat exchangers. It could be for water cooling, then ice makers, plate freezers, IQFs, blast freezers, etc., etc., etc. The next, now the first question is direct expansion system or flooded evaporator systems. Now remember the pH diagram which you saw. The direct expansion system, the refrigerant, when it is entering the evaporator, that is a constant enthalpy line, that is 0.3 to 4, and 0.4 was a mixture line. So the refrigerant entering the evaporator is a mixture of dry refrigerant and a wet refrigerant. As your evaporating temperature starts falling down, the percentage of dry refrigerant increases and percentage of wet refrigerant quantity decreases. As the refrigerant travels in the evaporator, it evaporates, and at the outlet, you get 100% dry refrigerant at the outlet because it has done all the work. The latent, it has been used, the refrigerant has been converted to a vapor. So dry at the outlet, this is a direct expansion system. In a gravity flooded system, what we do, after expansion, we have an accumulator. And in the accumulator, we separate out the gas and we take only the liquid and circulate it into the evaporator. So evaporator has liquid in the inlet and gas at the outlet, but entire evaporator is full of liquid. This is very, very important point in a gravity flooded system. So let us look at the direct expansion system. This is the coil. This liquid refrigerant, this is a thermostatic expansion valve with a superheat bulb, and the refrigerant, this is the evaporator coil or a direct expansion coil. But the next slide, if you see, it will be very, very clear. If you see this red portion, that is a mixture portion, and as the refrigerant is traveling from the top and going to the outlet of the bottom, you see this mixture of saturated liquid vapor is traveling, and it is only once through process. Once the liquid and vapor mixture enters the evaporator, till it goes out of the evaporator, there is no flow back. It travels only in one direction, and because of the superheat control, at about 85%, 90% area, when it covers, it becomes 100% saturated vapor, and the remaining portion of the evaporator is used for superheat. So this is important slide to be remembered. This is a pH diagram. Again, as I'm repeating this just to recollect, 3 to 4. Now, point 4 is important, that is inlet to the evaporator. As I mentioned, the left line is a saturated line, right side is a saturated line. So, point 4 is in between, that is liquid and vapor, that is part of the vapor. From saturated line to point 4 is a vapor, and from 4 to 1 is a liquid. This diagram, again, as I said, pH diagram is very, very important. As you go for lower temperature, I did mention that point 4 goes on lowering down and down, and therefore your percentage of gas goes on increasing and percentage of liquid goes on reducing. This is also an important point to remember. Now let us see gravity flooded system, what happens. In a gravity flooded system, as I did mention, there is in this accumulator, the liquid refrigerant is coming, there is a float control, and there is an accumulator. In the accumulator, the refrigerant vapor is separated out, and entire liquid, only liquid goes into the coil. So 100% liquid at the entry and liquid at the outlet, with some gas bubbles, because liquid will go on evaporating, and those gas bubbles will be accumulated in the accumulator and it will be sucked by the compressor. But liquid is traveling and there is a recirculation. Flooded evaporators, water liquid which is not evaporated again recirculates into the coil. And this is the flooded evaporator coil, red from the beginning and red at the outlet. So you see this is full of liquid. Now why I'm again and again repeating this? Because there is a significance. This is the pH diagram again of flooded system. Point 1 is a normal point, but in accumulator we separate the vapor and take liquid at 1 dash. So you see 1 dash to 1 is a big line compared to 1 to 2. Just remember this much. And therefore, in gravity flooded system, the circulation rate depending upon you require some static head to flow to take place, and therefore the circulation rate is around 1.5 to 2 times depending upon the evaporator design and the pressure drop in the evaporator. If you see W.F. Stoker volume, he will explain this, why this circulation rate goes on changing as per the evaporator design. And this is a gravity flooded evaporator. This is an accumulator. The slide is not very clear, but I wanted to show this slide just to show that it is full of liquid. The evaporator is full of liquid. Now, why gravity flooded system is better than DX system? This is what I want you to remember. It is the latent heat which we last time discussed, and we compared the latent heat of various refrigerants, and we found that ammonia has the largest latent heat next to water. So it is the latent heat which makes refrigeration work. And what is latent heat? Latent heat is the conversion of liquid to vapor. So higher the latent heat, more efficient is the refrigerant. So ammonia is the best refrigerant we saw. More the liquid refrigerant in the evaporator, more is the latent heat and more efficient, because more liquid will get evaporated. If there is a gas in the evaporator, gas does only sensible, and which is a very low element. In the DX evaporator, the refrigerant is a mixture at the entry, and the liquid can be 70 to 80%, gas could be 20 to 30%. It is the liquid refrigerant, when it gets converted into vapor, it absorbs maximum heat. The vapor does very little work. For example, just to give you a simple example, in terms of FPS unit, the latent heat of water is 970 BTU, whereas the specific heat of water or sensible heat of water is only 1. So latent heat is 970 times better than the sensible heat. So just to impress the point, I just gave the inform. Last time I had given the details of ammonia sensible heat and ammonia latent heat. In a flooded system, it is the liquid at the inlet and the liquid at the outlet, and hence flooded evaporators are more efficient. In DX system, there is no recirculation. Once the refrigerant enters the evaporator, it travels only in one direction until it goes out to compressor. In flooded system, there is a recirculation. So direct expansion system or a flooded system. Advantages of direct expansion system: quantity of refrigerant charge is low. Advantage of, because there is a gas and liquid, and with thermostatic expansion valve, you don't need an accumulator. So quantity of refrigerant is low. It is easier to operate and more compact. Therefore, all uses, room air conditioners, split air conditioners, everything are in DX systems. Can be used for low capacity system design, because the power consumption is not so very important. In a large systems, power consumption plays an important role. Air cooled condenser possible for very small systems, because air cooled condenser also becomes sizable, not too big. And of course, because of all these simplicities, the initial cost is pretty low of a direct test. These are the advantages. Now, what are the drawbacks? Less efficient, as we saw, requires synthetic oils, which are miscible with ammonia refrigerant, because we cannot afford to uh, uh, oil to come out of the system. It has to travel constantly from compressor to condenser, condenser to evaporator, and back to compressor. There is nowhere accumulation in between the system. So it has to use a miscible oil, which is a synthetic oil. And the most important point is, normally in a flooded system, as I mentioned, Moisture content into the ammonia systems, although is not desirable, is not detrimental. A little bit of moisture in the system does not stop the system. In a DX system, if there is a moisture in the system, your thermostatic expansion valve will stop functioning. So very important, control of moisture in the expansion valve and in the system is very important in direct expansion systems. Now let us see the flooded system characteristics and pump system characteristics. Now we have gone one step ahead. We have covered direct expansion systems. Now we are going to compare gravity flooded systems and pump circulation systems. Both are flooded systems. Still they have similar characteristics. But in gravity flooded system, as we saw, no pump is required. So there is no pumping energy. Only static pressure ensures that there is a continuous flow of the liquid. This system is normally used for a small size cold storages, very low, maybe one or two chambers, say 2000 ton potato cold storage. Up to that, you can use gravity flooded systems because there are only two cold rooms or at the most three cold rooms and 2 to 3 coolers, not more than that. And the system is compact. The air coolers and the compressors are not very far off from each other. So they have to be, air coolers have to be near to the compressor, and normally on the ground floor there is a machine room, or adjacent to cold storage there is a machine room. So it is very compact. Now let us see forced circulation system. This is my favorite system. I have given a presentation of this system in Nuremberg in Germany and in Macedonia also. So I will talk a little bit more on pump circulation systems, which are my favorite systems. The first forced circulation system, you will see there is a pump, ammonia pump, I have shown with a green arrow, and the evaporators. And the liquid is circulated into the evaporators by force feed, that is by pump. And then it comes to the accumulator, or what we call this vessel, not accumulator, we call it LP vessel, low pressure vessel. It is a low pressure receiver, like high pressure receiver. This is known as low pressure receiver. And from which the suction to compressor takes place. The liquid from condenser comes through a expansion device into the LP vessel. When to use overfeed vessel? Now the question is, as I mentioned, when there are more than 3 to 4 air coolers and we want equal distribution of refrigerant in all the coolers. If there are more coolers with gravity flooded, it becomes difficult because the pressure drops go on changing and adjusting becomes difficult. Processing area away from the machine room. The process, this is what happens in case of fisheries plants or meat processing plants or ice cream plants or a dairy plant, where your processing areas are much away than the plant room. And of course, for low temperature applications, again I'm going back to pH diagram. If you see on a pH diagram, low temperature means more gas and less liquid. In pump circulation systems, we circulate only liquid into the evaporator, like gravity flooded systems. So this is a simple circuit of a pump circulation system. There is a compressor. From compressor, the refrigerant goes to condenser, then to float control, which is on the LP separator. And from LP separator, compressor sinks the vapors. The liquid which is stored at a low temperature and low pressure in the separator is circulated by the pump into the evaporators, and then it comes back and falls into the separator. It doesn't go back to compressor. So the most important point to be noted is the compressor circuit is independent and the LP vessel circuit is independent. These are two separate independent circuits, and this LP vessel, just to again give you a common man's in language, it is like a corporation water tank which is at a very high level. So long as there is a water in the tank, every household, when you open the tap, you receive the water. If the corporation is going to clean the tank, then they tell you that tomorrow there will be no water supply. Similarly, when there is enough liquid available in the separator and at a particular temperature desired, then you don't have to worry. Your evaporators will always go on getting the liquid ammonia at a particular temperature, whatever you want. The compressor circuit is independent. This is the main advantage of LP circuit. This is an LP vessel. I'll not discuss the LP vessel design, but you see there are three switches. One is high level switch, one is compressor trip switch, and one is liquid level switch. These are the protection devices, and there is a oil pot. So the oil is collected in the oil pot and drained from the oil pot. Just keep this in mind. In next slide, I will explain you. And then these are two pumps, one working, one standby, and the pump is circulating liquid supply to evaporators. Now, the lot of people are not very clear what is circulation rate and overfeed rate. There is a confusion. Some people specify overfeed rate, some people specify circulation rate. Now let us see, actually when you talk about circulation rate, it is the circulation rate if it is 4:1. That means 4 kgs of refrigerant you are circulating through the system. Out of that, evaporation will take place only equivalent to 1 kg because that is the latent heat transfer taking place based on your load of the system. So 1 kg will get evaporated and 3 kgs liquid will return to your LP vessel. So there is a 3 times excess flow than what it evaporates. So that is 4:1 ratio. And overfeed rate, when we call 3:1, that means we are overfeeding 3 times more liquid than required. Again, the total is 4 kg. Evaporation is 1 kg of liquid and liquid return 3 kg. So when you are specifying, be very careful whether you want circulation rate or you are mentioning overfeed rate. These are the recommended rates as per the evaporator designs. Blast freezers, air coolers, in carbon dioxide 1.2 to 2, ammonia 3 to 4, R22 2 to 3, etc. etc. I will not go into the plate freezers. If you see, plate freezers requires a lot of circulation rate. Now I had a doubt, I checked it everywhere, which textbook gives this explanation. No textbook gave this explanation why plate freezers require such a high flow rate. Then, because I have done a lot of plate freezer plants, 30-40 plate freezers in single plant like Gadre Marine, Mangalore plant, etc. So if you see the construction of a plate freezer, it is a square aluminum tube, and the cross section of the aluminum tube is much bigger than the diameter of the air cooler tube, and therefore to maintain the same velocity you require higher flow rate. This is the conclusion which I have drawn. I have not seen this conclusion in any other textbook. It only mentions that flow rate for plate freezers has to be higher. Anyway, let's go back to the next slide. Now this slide is prepared by me. It is not available in any textbook. I will now repeat once again that many slides out of this presentation are collected based on my experience from various sources, my friends, my colleagues, their presentations, etc., as well as from textbooks, etc. But few slides I have prepared myself, as I showed you that TH enthalpy diagram and this gravity feed and so force feed system. Most of the air cooler manufacturers will say that the performance of the air cooler is the same, whether it is gravity feed or a force feed, and their ratings are not different. But in reality, force feed system performs much better. Why? Because you see in gravity feed system, when the refrigerant is boiling and the flow rate is 1 to 1 or 1.5 to 1, the gas bubbles, they go around the wall, and gas density being very low, they stick to the wall. Place, constant evaporation is taking place, and therefore pump circulation systems in reality perform much better. Advantages. Now we will see the advantages of overfeed system. Higher circulation rate, so improved heat transfer by completely wetting internal surface, as we saw in earlier slide. Compressors are protected from liquid slugs because compressors are not connected with your fluctuation of load, that is connected with LP vessel. Compressor will go on receiving only from your LP vessel. So compressor is so better compressor operation, and since LP vessel is kept in the machine room, the distance between the compressor and LP vessel is very less. So there is very less superheat, and therefore compressor superheat is being low at the suction. The discharge temperature also becomes low and compressor efficiency improves. Efficient freezer operation. Freezer operation is decoupled from main refrigerant, and you can control the flow to each evaporator in the same ratio 3 to 1 or 4 to 1 based on your flow regulating valves. Pumped refrigerant feed independent of fluctuating condensing temperature. Whatever may be the condensing temperature, your LP vessel is not affected so long as it has liquid, let us say at minus 40 degrees centigrade and at a 0.6 bar pressure, which is required for minus 40 degrees freezing plants, that is plate freezers, blast freezers, IQFs, etc. Pump refrigerant feed is independent of fluctuating condensation temperatures, as we saw. Minimum superheat since LP vessel is near the compressor. We saw this. Now I showed you the slide of LP vessel. Oil recovery is simple. You don't have to recover oil from each and every evaporator which is required in the gravity flooded system. Oil recovery becomes because you have to recover oil only from one point, that is oil drain point. With simple controls, evaporators can be defrosted with hot gas defrost. This is an independent subject. It will take one full lecture to discuss hot gas defrost. We will not discuss it at this stage. But the flash gas is removed in the LP vessel before liquid enters the evaporator. And this gas is then directly drawn by the compressor. The next slide, the troubleshooting is easier since LP vessel and evaporators are two independent circuits. So long as I mentioned, there is liquid in the LP vessel at a particular temperature, then you don't have to worry anything about the compressor circuit. That means it is delivering the correct output. It is giving you the temperature, it is giving you the required liquid quantity. Now, how to use that liquid? is a secondary circuit, that is LP vessel to your air coolers or downside equipment. All major equipment is in the plant room, so it is for operator it becomes easier. He doesn't do the running around. Compressor life is extended because there is no liquid going to come to the compressor, because it is an independent circuit and not dependent on fluctuation of loads. You have to be careful in designing the pipelines. There is a separate presentation on how to design pipelines from LP vessels to compressor suction, because many times people get liquid into the compressor even if LP vessel is there. So LP vessel design and suction line piping is important. Liquid feed is more reliable, as I mentioned. Automatic operation is very convenient. Next slide. Oil does not accumulate in the evaporators we discussed. Uniform distribution of liquid in all the evaporators does not require, each evaporator does not require independent accumulator, level controller, expansion valves, etc. It is only in one place, more suitable for low application because flash gas is removed, as we discussed. So higher percentage of gas after expansion. Now let us see what are the drawbacks of this system. There are some drawbacks also. See, in world nothing comes free. Anything good is there. There is always bad thing. We get many times pleasure and many times we get also disheartened because of some things which don't go correctly as per our. So this is a balancing. So some disadvantage along with the good point comes. What is the disadvantage? Because of the introduction of LPSL, the refrigerant charge in the system is much higher. Due to higher flow rates, liquid to the evaporator liquid line and wet return line, the line sizes are much bigger, both liquid line size and the wet return line size, than the suction line or normal liquid line. Now, when the line is bigger, naturally these are low temperature lines, so insulation cost is much higher. Longer liquid supply lines from machine rooms, they also need to be insulated. Normally, we don't insulate liquid lines because expansion takes place near the evaporator. But here the expansion is taking place much earlier before the LP vessel. So the liquid line is a cold line and needs to be insulated. So installation cost is higher. Then extra power is required for the pump, and normally it is compensated by better efficiency, and power required in very big plants also I have seen not more than 3 to 5 kW. That is the maximum power required for the pump. Pumping unit requires maintenance. Naturally, when you add pump, some maintenance will be required, and pump installation is very, very critical, and we have to ensure there is no cavitation. These are the drawbacks of pump system. A separate presentation on pump system of 1.5 hours can be easily done. Will not go into the details of pump circulation system. The problem of liquid hammer takes place many times because of the improper designing of piping and defrosting sequences of the air coolers, hot gas defrost. Liquid traps should be avoided, and many times it is required because the liquid line being long and liquid is not expandable or contractable, you may require a safety valve in the liquid supply line. So these are the drawbacks. Now we go to our next presentation, which is known as low charge systems. Now low charge systems are low ammonia charge systems. This is a recent development because of the toxicity of ammonia. People are trying to design systems where the quantity of refrigerant is reduced to a maximum extent. So, what is the definition of low charge systems? A low charge system is defined whichever system having 1.3 kg of ammonia per kilowatt of refrigeration. This is maximum quantity of ammonia in the system. If your refrigeration charge is lower than 1.3 kg, it is low charge system. A normal gravity flooded system, if you remember those who are old timers, they used to say 10 pounds per ton or about 3 to 4 kg per kilowatt. So this was the yardstick earlier. Now it is no longer there. 1.3 kg is the deadline. Now next slide is important. You can see there are systems which are available now with 0.3 kg per ton. Can you imagine? Imagine it's a very, very low charge. They use high side float and they eliminate HP receiver. The next system also is available, which won the first prize in ASHRAE exhibition last year before last, designed by Star Refrigeration UK. This is an art. These figures I have taken from ASHRAE Journal, January-March 2017 issue, where this article has appeared. You can, those who are interested can read this article. Now, what are the design components for low charge systems? PHE condenser and chiller. Both condensers and chillers are not shell and tube. Shell and tube has large ammonia volume. PHE, plate heat exchangers, require very low charge condenser in the chiller. Then high side flow. So ammonia receiver is totally eliminated. The maximum charge is in ammonia receiver, which is deleted. Then now the latest designs are microchannel heat exchangers, especially for the evaporators. So evaporator charge becomes very low. Direct expansion evaporators, air-cooled condensers, aluminum air coolers, compact coolers, miscible oils for DX systems. Then cascade system, instead of using ammonia for everywhere, use ammonia only for high stage and secondary fluids like brine, carbon dioxide, CO2, etc. Other propylene glycol, ethylene glycol in the low side. So you reduce the charge of ammonia. One piece factory made units for roof mounting. Very compact units are now developed, which are roof mounted. I will, in my next presentation, I will show you all those things, or when my presentation is there on air conditioning, ammonia for air conditioning, I'll go into more details of this. Then LVS system, which I mentioned just now. Now I must thank here, and I must make a mention. As I mentioned, I have borrowed quite a good amount of slides from elsewhere. And this slide is from DC Refrigeration Private Limited. Mr. Vani, who is the owner of this company, and he is specialized in designing low charge ammonia systems using high side floats. So this is the pH diagram from his, borrowed from him. I have taken his permission. Before making this presentation, I have talked to him, and he has very kindly consented that I can show this slide. I thank him once again for his consideration. The next slide is a little complicated, but he has calculated in great details the refrigerant charge in suction line, discharge line, liquid line, accumulator, ammonia receiver, PHE condenser, PHE chiller, etc. This is a conventional 350 TR capacity, and the refrigerant charge, if you see, is 583.24 kg. This is the total refrigerant charge in a standard conventional system, ammonia charge system. Next, if we go, this is a high side float. These floats are available from two companies, WIT or Danfoss from Denmark, also I don't know whether any Indian company is also making these floats, but these are normally imported from these two companies. And this is, look at this, there is no receiver in this system. The earlier slide you saw, there is a receiver in the system, this central in the system. In this system, there is no receiver. This is a high side float. So whatever is liquid is formed in the condenser directly goes into the expansion device and in the PHE. So the entire charge of receiver is eliminated. Rest of the system remains same. Instead of low side float, we have a high side float now. In our centrifugal machines, we used to use this high side float. Anyway, when I was making centrifugals, Hitachi centrifugals in Kirloskar. Now this is a low charge system, same 350 TR, compressor, condenser, etc. all again recalculated, and you will see only 186 kg charge is required. If you compare these two slides, against 583 kg, you require only 186 kg ammonia charge. So it is very low charge system and very popular system gaining ground. This is a photograph again taken from Mr. Vani. This is the system using ammonia receiver. This red vessel below the condensers, you can see ammonia receiver. Then this cooling towers, etc., etc. And this is the system without receiver. This is a low charge system. There is no receiver. There is only high side float. This is LVS system. I will not go into the details of LVS system much because this is a patented system by JBT, and they claim that these are the advantages. Can be installed in few days, etc. Fully automatic controls, compact design, requires little floor space, fast temperature pull down, etc., etc. No refrigerant pump required. I have not used many of these, so I won't be authoritatively able to talk. But in one or two places, I have seen these systems in Pune. These are being used. It can be used only if there is a one process. If there are two processes, then it cannot be used. You have to use independent systems for two separate plants. Whereas with ammonia flooded systems, you can use 2 or 3 systems together. Or in gravity flooded system, you can maintain with the same high side equipment one room at -20 degrees centigrade, one room at -5 degrees centigrade. Now we go into a very important discussion, two-stage systems. We discuss up till now single-stage systems, gravity flooded, pump circulation, and low-charge systems. Now we discuss two-stage systems. Two-stage systems, when they are used, when the discharge temperature of the system plotted on a PI diagram exceeds 140 degrees centigrade. Saturated condensing temperature minus saturated temperature evaporating is more than 50 K or 50 degrees centigrade in ammonia, and in R22 more than 70 K. So we have to go for two staging. For same pressure range, ammonia may require two staging system, whereas R22 you can use single stage. Why? Because last time we discussed ammonia's index of compression is 1.31. So the discharge temperatures for the same pressure ratio in case of ammonia are much higher. And therefore, to protect the oil quality, we may have to use two-stage systems. Cascade system is used using same refrigerant but different high stage, low stage refrigeration loads. When cascade system is used, when there are two separate loads, high side load is different, low side load is different. There is no point in using common system because system will be more expensive. So this is possible. Cascade when different refrigerant for high stage and low stage. You can use different refrigerants. For example, in HAL Nasik, I designed a plant where I used a cascade system and 3 different refrigerants. R12 for high stage air cooled, R22 second stage, and R13 refrigerants for the air coolers with 3-stage operation. So you can use for 3-stage operation or 2-stage operation. Then you have to go for cascade. Now 2-stage systems I have already discussed. The temperature difference 50. Now let us say this is a single stage system. Common compressor, condenser, evaporator, expansion valve. And as I mentioned, at the end of the compression, ammonia is 1.31, whereas R22 and other 134A are much lower temperatures. Therefore, we need to use 2-stage system. Now in 2-stage systems, there are 3 types again. Which are the 3 types? Liquid injection in the interstage cooling. Closed interstage cooler vessel. Now this is becoming a little complicated, those who are listening to me, but kindly, since I have to cover this subject, I am covering this. Those who are using it, most of the senior people are using these various systems. For them, it is a known thing. And open interstage flash cooler. Let us see what is interstage gas cooling. What happens in a 2-stage system? Either you can have 2 separate compressors or a uni-built compressor. This slide shows a uni-built compressor. And what happens? The condenser liquid from 0.6 is taken. There is a thermostatic expansion valve, and a little bit quantity of liquid is expanded and injected into the interstage cooler from 0.4 to 3, with the result that the superheat of the gas is removed, and again you come to the saturation line, very near to the saturation line, as you can see again in pH diagram from 3 to 4. And then again you compress in the high stage from 4 to 5. So your 5 temperature is much lower if you had gone from 2 directly to 5. That would have been 5 dash, which point would have been very, very high. So in 2 staging, we have reduced this superheat in the intestine and we have recompressed the gas. So this is a injection interstage cooling system. What are the advantages of interstage cooling system? It is simple, inexpensive, no extra oil separator is required in high stage and low stage. One oil separator is good enough. Trouble-free oil return to the system. Saving in floor space, you don't require interstage cooler or other equipment. Easy to control and suitable for all refrigerants. The cost compared in 3 systems, this is the lowest cost. What is the drawback? No subcooling, so less refrigerant capacity. If you see here, pH diagram from 6 to 8, there is a direct expansion. 0.7 does not, 0.7 is a mixture point. It doesn't come to saturation line. Operating cost higher compared to the other system. The power consumption is higher. Expensive per unit cost. Anyways, small capacity plants, ammonia plants, installation is very simple. Where you don't have very trained operators, I would suggest use interstage gas cooling, liquid injection for a small system. The next system is a very, very important system, open flash interstage cooling. Here what you do, you have a separate vessel. You don't directly inject the gas with a liquid, you separate out. There is a mixing vessel which is known as open flash, where your discharge of high stage and this suction of this thing is mixed together, and then suction is taken to the compressor from this interstage flash cooler. So this interstage flash cooler, the discharge of the low stage is again mixed into this vessel. So there is a full mixture. So therefore the mixture comes to the saturation point, 0.4 lies on the saturation line. If you see, and 4 to 5 is the compression. But the most important point to see the line 6 to 7. 6 to 7 is expansion. It would have gone down straight in a in a liquid injection. But now here, because of mixing, this 0.7 shifts to 8. And again, we get a saturated 100% liquid which goes into the evaporator. So this pH diagram, as I mentioned, learning pH diagram is very, very important. The advantage of open stage interstage cooler: maximum capacity, minimum power consumption, maximum COP, entire operating cost is low. What are the drawbacks? Interstage cooling section expensive, requires shut-off valves, separate oil separator, HP suction strainer, more controls. You require more floor space for accommodating this interstage cooler. Then a very qualified operator is required. A system has to be fully automatic. It cannot be operated manually because operators' mistakes can lead to compressor breakdowns. Large refrigerant quantity, low pressure difference after the in the expansion valve because of the interstage. You bring down the pressure to interstage and then you expand it. So the expansion valve has a less pressure drop. Risk of flash gas, flash cooler in engine room. This is very, very important point. Flash cooler has to be, or interstage cooler has to be kept above LP vessel. And this is a big drawback in many cases because our plant room height is 10 feet and 10 or 12 feet. And the LP vessel itself occupies about 7 to 8 feet. So further height above this is not possible, and therefore many times LP vessel or this interstage flash cooler has to be kept on the first floor or outside the machine room. Or while designing the machine room, you have to ensure that it is at least 15 feet high to accommodate this. Why this is required to be kept above the LP vessel? Because the interstage pressure is very low, about 0.6 bar, and LP vessel pressure is nearly zero or minus. And therefore, if you take the pressure drops into this liquid line, many times the problem of liquid coming to LP vessel or filling up becomes a problem. Therefore, filling up of LP vessel can be done by gravity. Therefore, interstage cooler has to be above the height of the inlet of the LP vessel. Application: optimized system, large minimum size plants where the cost has to be minimum. This is a two-stage closed interstage system. We have discussed this. If you see this 0.6 to 9, again it comes back to saturation line and then the expansion takes place. And this 0.3 comes to 0.4, which is again a saturation line. Now we go to the third last system, which is closed flash interstage cooler. This system I would recommend to all those who are going to install the plant first time, because this is much easier. Your pressure drop across the valve is much higher and there are no problems of compressor breakdowns or other problems. You can operate the system easily. Capacity is somewhat lower than open flash cooler. Specific power consumption is higher. Interstage cooling is more expensive because there is a coil inside the interstage cooler. There is a coil, and all drawbacks of open, that is, it requires two oil separators, etc. We'll go a little faster. This is a comparison of interstage cooling systems, and I will show the same operating conditions. Liquid injection system, closed cooler system, and open flash cooler system. If you see, these are the capacities of the systems. Open flash cooler is the maximum capacity, and COP, kW per ton, power consumption, is the least. So if you take this difference, and if it is a 100 TR plant, 16 hours operation, 30 days running per month is a process plant, 8 months per annum operation, uh, you will find so much kilowatt saving, and current cost of 8 rupees per kilowatt, you save nearly 5,65,000 rupees per year. Anyway, we go to the last system, which is a cascade system. Just 5 minutes are left, so I'll cover this. Cascade refrigeration system, you see there are two separate pH diagrams. So there is an in the interstage, there is no mixing. There is a separate heat exchanger. And when you introduce a separate heat exchanger, naturally for heat to flow, you require a delta T. And therefore, cascade system, the power consumption compared to open flash cooler system is much higher. Is slightly higher, I would not say much higher, but I have told you when cascade system is essential. When two different refrigerants are to be used, or the secondary system like supermarkets has to be with carbon dioxide and high stage with ammonia, then you use cascade systems. And this is a cascade system layout. This diagram will be available to you on the website or my presentation. What are the applications and advantages? Advantages, simplicity of operation. Two different loads, high stage load could be different, low stage load could be different. Regular skills are enough to operate the plant, not like open flash cooler where you require skilled operators. No oil circulation recovery problems because every circuit is independent. Different refrigerants can be used. A three-stage cascade, as I mentioned, is also possible. Cascade condenser is a penalty. Therefore, the power consumption is more. First cost is higher because you add one more heat exchanger. Expansion valve pressure drop is less. The valve is bigger. This is an ammonia CO2 cascade system. If you see the high stage 30 degrees condensing R717, minus 12 degrees evaporating, and condensing minus 12 degrees is a cascade low stage system. Minus 7 degrees centigrade is the condensing temperature for high stage. So minus 12 and minus 29 minus 20 degrees centigrade is a low stage. If you compare, this slide is theoretical slide. It's not, you cannot operate the plants like this, but just to highlight the point, I said I will cover this slide. In reality, in practice, this does not work. But for comparison purpose, I have taken 50-ton plant with, this was prepared long back, so it is in steel FPS system, R22, 105 degree Fahrenheit condensing and 40 degrees, 5 degrees centigrade evaporating. You will say single stage power required is 120.6 kW, COP is 1.95, compressor displacement, you require a large compressor, and the discharge temperature, if you would have used this single stage, it would have gone to very, very high, 190 degree Fahrenheit. If you use two stage, LP and HP power consumption, two separate compressors is different. COP of each compressor will be different. Compressor displacement of each compressor will, because the density of refrigerant will vary, and the discharge temperatures of booster compressor and high stage compressors will be separate. The total power consumption will be 102 as against 120 kW and or 120 horsepower and 102 horsepower. And if you use cascade system, you have to use, your power consumption will be 114. As I mentioned, it is more than two stage. but less than single stage. So this is a cascade system. Many consultants, well-known consultants, tell the end user, oh, cascade system, you will get lower power consumption. This is a wrong statement. Cascade condensers, cascade systems will always consume more power because of additional heat exchanger in between the two stages. So this is slide just for the sake of comparison I have prepared. I had requested Ishre to give me a time of 1.5 hours. I think I have taken 1.5 hour full time. I have gone little faster. As I mentioned, every system you can take 1.5 hours separate lectures on open system, open flash system, hot gas defrosting, piping design, etc., etc. But that is not the objective of today's seminar. We just wanted to just touch upon the various systems. And I thank once again Ishre for and all the patient listeners. If you have any questions, as usual, send the mail to Ishre and they will forward it to me. I will reply all your questions. Thank you very much. I thank Ishre once again and all of you for giving me this opportunity. Our next presentation will be various designs and how the improvements have taken place in compressor designs, in condenser designs, in evaporator designs, in controls, etc. So we'll be discussing the equipment advances in our next seminar. Thank you very much. I hand over to again to yeah.
Thank you, sir, for the elaborate presentation, wherein you covered from the basics to the latest technology. We had a good we came to know more about the latest low charge ammonia refrigeration system, as well as the principles. We went through the pH diagrams and single stage, two stage. It was really very informative, and I'm sure we would not have seen such presentations uh, earlier. Such a large, such a big presentation for 90 minutes covering the total basics of refrigeration and its applications. I would like to request all the audience here to send your questions to us, and we'll be glad to get back to you with whatever response we could solve or give response to your questions. As we have already crossed our time of 1 hour, of course, this was for a 90-minute program. I would thank you all for be participating in this program, and now I request you all to again log in on Friday, where we will have more in-depth information about the various equipments like compressors, condensers, evaporators, and I'm sure some amount on the expansion valves. And I'm not sure what else new things will come up, as we have seen many new things coming up in this presentation. So let's keep guessing, and I request you all to join again coming Friday. Ravi, you have anything to convey?
No, sir. Thank you.
Thank you very
Okay.
much. And Manjunath and all the people. And I think I will sign off now. Thank you very much. All the best.
Yeah. Thank you, sir. Thank you.
Thank you.
So next